Hello, so today we're going to talk about the concept of the chain rule in relation to derivatives. Now, as the name implies, the chain rule is a chain of derivatives from one particular function. Now, this is going to be a little more complex than your just usual product or quotient rule, so you need to make sure you're paying attention and you're being careful. So what's happening is we essentially have two different functions going on. We have the composition of functions. Y equals f of u, where u is a differential function, and then u equals g of x, a separate differential function of x. So we're really dealing with y equals f of g of x. If we were doing the composition of functions from pre-calculus, that's what's happening here. So the way the derivative works is this. We're doing f of g of x. We must first take the derivative of f, that original function, with just the g of x saying where it is, but also then times the inside, the derivative of the g of x function. So there has to be two separate derivatives, the derivative of the original f function and the derivative of the inside g function. So we need to take a look at how that actually applies to actual problems. So this right here is an example of f of g of x, where if I wanted to separate this out, the f of x is really just like x to the sixth power. And then the g of x part is the inside 3x to the fourth minus 7x. So what we're going to do is, to find this derivative, we first ignore the inside. This is a power rule. So the exponent goes in front. The inside stays the same, and I decrease the exponent by 1. The exact same way you would take the derivative of x to the 6th and make it 6x to the 5th. But now the difference is, the inside part itself still has a derivative. So we must multiply by the derivative of the inside, which is 12x cubed minus 7. And that's how the chain rule works. So it's the chain of derivatives. The derivative of the original power rule times the derivative of the inside of that power rule. So again, just to recap, if we're raising the expression to a higher power and I want to take that derivative, I apply the power rule to the expression, moving the exponent in front, the 6, and decrease the exponent by 1. But I must then also apply the chain rule to the inside and take the derivative of the inside portion. If you would like to turn the 6 into the 12x cubed and the 7, that's fine. There's no need. You can leave it the way it is right here. Same thing for this problem. We have f of x equals the fifth root of 9x squared minus 5 to the third power. So first off, I'm going to write this as a power. So this really is a 3/5 power because I'm taking the fifth root but cubing the inside. So it's 9x squared minus 5 to the 3/5 power. Now again, the way the chain rule will apply to this particular problem is I apply the power rule part first. I bring the exponent in front, 3/5, rewrite the inside, that cannot change, and then I decrease the exponent by 1. 3/5 minus 1 is a negative 2/5. I then multiply by the derivative of the inside, which is simply 18x. If you would like to write this so you no longer have negative exponents, 3 times 18 is 54, so it's 54x times 5 times 9x squared minus 5 to the positive 2/5 power. It's the same answer. Both of them are seen as correct. This right here is probably a simpler version because it combines the 3 and the 18, puts a 5 on the bottom, and also puts a negative exponent on the bottom. So it's perfectly acceptable. But again, the way the chain rule, the important part, the calculus part, because the rest of this right here is just algebra. The calculus part is, again, as always, write it so it's in exponential form. Derivative of the exponent comes in front, then decreases by 1, and then the inside itself gets a derivative. So for this problem, I don't want us to think of this as a quotient rule, again, because it's just simply a monomial term up top. You should rewrite this as 6 times 4x squared minus 5 to the negative 5th power. This is a much easier application of the chain rule than it would be to actually apply the quotient rule to this problem. So what I want you to do now is, since we now have talked about the chain rule for two different examples, I want you to use your chain rule to take the derivative of this expression right here. 6 times 4x squared minus 5 to the negative 5th power. So I'm going to pause the video, or you should pause the video, and while you work on that, once you're done, unpause it and see what my answer actually is. Okay, so after we wrote it as 6 times 4x squared minus 5 to the negative 5th power, the chain rule applies. So negative 5 goes in front, so 6 times negative 5 is negative 30. we write the inside the way it is, decrease the exponent by 1, that's why it's negative 6. And then the derivative of the inside is just simply 8x. To write it so it no longer has a negative exponent, negative 30 times 8x is negative 240x, so that goes up top. On the bottom is our 4x squared minus 5 now to the positive 6 power. So that's the way this is working with our chain rule for the different problems like this. You will find sometimes chain rule will require you to actually use the quotient rule. Generally, you want to try and avoid doing that. Just like if you could avoid using product rule for this, you would definitely do that as well. The key is trying to make it as simple as possible, because the calculus itself really isn't that bad, but the algebra behind using some of it can get a little more complex. Now, the chain rule also applies to different trig functions. If you look back at your notes from all the different times you did derivatives with trig, it was always sine of x, or cosine of x, or tangent of x, just x. The angle was just simply x. So the chain rule also applied for trig problems, and the angle was no longer x. So this way this works is we still take the derivative of our trig, derivative of sine is cosine, the angle can't change, but now we must also times the derivative of the angle. Derivative of the angle 5x is just simply 5. And then to write it properly so it doesn't look weird, because again the angle times 5 doesn't work out, I'll put the derivative of that part in front. So it'll be 5 cosine of 5x. In the future, what I'm going to do is to make sure it looks a little bit better from the very beginning, I'm going to do the derivative of the angle part first, and then do the derivative of the actual trig problem. Okay, so it's 5, derivative of the angle, times derivative of the actual trig, cosine of the angle 5x. The angle itself cannot change. It must always be that angle. The derivative is not involved with that. So same thing here. If I want to do the derivative of cosine of the angle 2x cubed plus 5x, well, the derivative of the angle part is 6x squared plus 5. That must be multiplied by the derivative of the trig part, which is negative sine of the angle 2x cubed plus 5x. So it's negative of 6x squared plus 5 times sine of the angle 2x cubed plus 5x. And there we go. You must always deal with the fact that you must do the derivative of the angle and the derivative of the trig problem itself. So you got to be careful with these. Now this is also still technically a chain rule problem. We're doing tangent squared of x. So another way to look at this is not just simply tangent squared. I would write it like this: tangent of x squared. Because the reason why I want to write it like this is because now I can see this as a power rule problem with our chain rule. So the way the power rule works is we bring the exponent in front, so the 2 goes in front, and then times tangent x, now to the first power. And now times the derivative of the inside, well, derivative of tangent is secant squared. So right, so it's not as weird looking, it's 2 tangent x, secant squared of x. That's the proper way to write this particular derivative. So, in addition to the fact that you must deal with the fact that the angle itself, if it has a derivative, you have to apply the chain rule there. If you're raising a trig function to a higher power, you should think of it as the trig function in parentheses raised to that power, so you can use your power rule with your chain rule. And that's what we're going to see right here. So I'm going to rewrite this as secant of the angle 4x squared minus 2x cubed. So, the way the derivative works, because it's a power rule, the exponent goes in front, and I rewrite the exponential part as secant 4x squared minus 2x. It's now raised to the second power because it's decreased by 1. And now then the derivative of the inside. Derivative of secant is secant tangent, so it's secant of the angle 4x squared minus 2x times tangent of the angle 4x squared minus 2x. We also can't forget we now need to multiply by the actual derivative of the angle itself. So derivative of 4x squared minus 2x is 8x minus 2. So before I do anything else, just a quick review how we got to this. I rewrote this as secant of 4x squared minus 2x to the third power. So I can then use my chain rule. The 3 goes in front, because that's how the power rule works. And I decreased it by 1. That's why it's now in the second power. Nothing on the inside can change. Now that I've done the power rule with that, I now then take the derivative of the inside. Derivative of secant is secant tangent. That's why it's secant of the angle 4x squared minus 2x times tangent of the angle 4x squared minus 2x. That's the derivative of secant. Then don't forget also, since I'm taking the derivative of a trig function with an angle that has a derivative, we must take the derivative of the angle itself. That's where 8x minus 2 came into play. So what I'm going to do is I'm going to rewrite this, where I'm going to distribute 3 into the 8x minus 2. So that'll be 24x minus 6. And then if I have secant squared and a secant, that's really secant cubed. So it's secant cubed of the angle times tangents of the angle. And there's the proper way to write the derivative. You will generally find with derivatives of secants is the power for secant stays the exact same. You're also then going to include the tangent as well. So if this was secant to the 7th, you would find your final answer would have a secant to the 7th, but then also with a tangent. So you have to be careful with some of these trig problems. They can get a little tricky if you're not paying attention. Always rewrite it as the higher power, and then just go step by step. The exponent goes in front, decrease it, derivative of the inside, derivative of the angle. This right here is the example of how I'm going to use the product rule to combine with our chain rule. Because I have two separate functions. I have x squared, and I have the square root of 1 minus x squared. So first off, again, I should write them as powers. So I have x squared times 1 minus x squared to the 1/2 power. So from here, I do my derivative of the first parts. Derivative of x squared is 2x, so it's 2x times 1 minus x squared to the 1/2 power. And then plus the first times the second. So now this is now a chain rule, so the exponent goes in front, 1/2. 1 minus x squared, I decrease it by 1, so it's negative 1/2. And then times the derivative of the inside, which is negative 2x. So there's nothing really going on with this first part, just simply 2x times 1 minus x squared to the 1/2 power. Because this has an exponent, I can't distribute the 2x in, so it's got to stay the way it is. Here, again, I can't really change the negative 1/2 part of it, but I can do an x squared times 1/2 times a negative 2x. When I do that, I get a negative x cubed. X squared times x is x cubed. 1/2 times negative 2 is a negative 1, hence negative x cubed. Times 1 minus x squared, it's negative 1/2 power. And I'm going to stop right there. When we talk about actually applying these derivatives, and we actually use them to solve different problems, we will go further than this. Because we'll need to set equal to 0 and solve, but for right now, there's no need to go any further. This is the derivative. Going further just is a different way of writing it, which is useful for solving, but not really useful for actual derivatives. So like I said, we'll stop here. Later on, when we talk about applying them, we'll go further. So again, we used our product rule. We wrote it as an exponent, and then did our derivative of the first, times the second, plus the first, times the derivative of the second. And this part right in here is where our chain rule got applied. We're moving the exponent in front, decreasing it by 1, and then doing the derivative of the inside expression. This right here, again, we could think of this as a quotient rule, but I'd rather not. I'd rather rewrite this as x times x squared plus 4 to the negative 1/3 power. Again, this really is x squared plus 4 to the 1/3 power, but then since in the denominator I can write as a negative 1/3 to write it as a product rule instead of a quotient rule. Quotient rule will still give you the exact same answer. I just generally find product rule to be a little bit faster to work with. Just my personal preference. So there's our first function, there's our second function. So I want you to go ahead and try using the product rule on your own to use this right here. You should be comfortable with the product rule and should be getting a little more comfortable with the chain rule at this point. So again, derivative of the first times the second, plus the first times the derivative of the second, and then be careful using the chain rule when you do this derivative. So I'm going to go ahead and pause. You work it out once you have an answer, or once you get stuck, if that happens, unpause it to see what I have. Okay, so for this derivative, your final answer should be x squared plus 4 to the negative 1/3 power, minus 2/3 x squared times x squared plus 4 to the negative 4/3 power. Again, the way it works is it's our product rule, so we do the derivative of the first. Derivative of x is just simply 1, times our second function, x squared plus 4 to the negative 1/3 power. And then plus the first function times the derivative of the second. And this is where the chain rule comes in, so the exponent comes in front. I rewrite the expression, but decrease the exponent by 1. And then times the derivative of the inside, which is 2x. So this first part is just simply, again, the x squared plus 4 to the negative 1/3. Here, when I combine x, negative 1/3 and 2x, I get a negative 2/3 x squared. And again, if I'm talking about applying derivatives, I'm going to actually go a couple steps further. But that's actually solving z equals 0. No need to actually do that for this particular problem. Alright, last example. This now is where we're going to be required to actually use our quotient rule to solve this problem. So I'm doing f of x equals 3x minus 1 over x squared plus 3 to the third power. So again, the chain rule is still going to work out because I'm doing an expression raised to a higher power, where the expression has a derivative. So again, the exponent comes in front, and then I rewrite the inside. So 3x minus 1 over x squared plus 3. I now decrease the exponents. But now I do the derivative of the inside, and this is where the quotient rule comes into play. So quotient rule is derivative of the top times the bottom minus the top times derivative of the bottom all over the bottom squared. So from here, we just need to simplify the top expression to combine things to get the final answer. So again, it's 3 times our 3x minus 1 to the over x squared plus 3 to the second power. Up top, when I distribute, we get 3x squared plus 9 minus 6x squared plus 2x over x squared plus 3 squared. Now, to write our final answer, our numerators will write together and our denominators will write together. So we have 3 times 3x minus 1 is being squared. And in this piece, well, 3x squared minus 6x squared is a negative 3x squared plus 2x plus 9. And on the bottom, we notice we have the same expression, x squared plus 3 squared, x squared plus 3 squared. So I can combine that to 1, x squared plus 3 to the fourth power. So that's how the quotient will apply here with the chain rule. Again, I still use my chain rule. The exponent comes in front, rewrite the expression, decrease the exponent by 1. I then apply my quotient rule, which we've already seen multiple times. Derivative of the top times the bottom, minus the top times derivative of the bottom, all over the bottom squared. The key is then to simplify it further from there to combine the top, and then rewrite as one single fraction by having all the numerators together and all the denominators together. You'll find in these particular problems, your denominators will be the same expression. The key is just adding the exponents together to get the one single expression. So that's the chain rule. That really is the most complex way of dealing with derivatives. All the other derivative problems we're going to talk about are just different types of rules for derivatives and how to work them out. They really won't be more complex than this. So next time we're going to talk about related rates. Not related rates. Implicit differentiation. Talking about taking derivatives with respect to x, but involving other variables. So if you notice, for the most part, all our variables are either x's for these problems, or maybe t's for time and stuff like that. We're going to talk about how to deal with when it's x and y and z and other things going on. So I will see you next time.